Now that we've talked about the standard normal distribution, I want to cover just a real brief topic, the idea of transformations. Basically, there are times when our data need to be transformed. When this occurs, let's say we're doing some kind of study and we want to look at ACT scores and GRE scores. Well, those are two very different scales, and it's sort of like comparing apples and oranges. I don't have any way to sort of make those meet in the middle where I can compare GRE scores to ACT scores. So we've got to make some kind of transformation. When we talk about transformations, one of the most basic kind, and this is the one we'll deal with primarily, is the idea of linear transformations. I've got a couple of things here, but really I just want to give you the nuts and bolts of linear transformations. When you add, subtract a constant, it does the same thing to the mean. It will add or subtract, multiply or divide by that same constant to the mean. However, those changes don't affect the standard deviation or variance. In the end, this third point means that it doesn't change the shape of the distribution. So if you have a leptokurtic, unimodal, negatively skewed distribution, you will end up with that same distribution after we conduct a linear transformation. All it does is tries to shift the mean one way or the other. What we're going to do is try to create a new scale where we can compare the mean ACT scores to the mean GRE scores and sort of try to align those and see how the distribution shapes up. Okay, so the way that we would do this, the most common way, is what we call through z-scores. And it gives us the ability to compare different scales or different values from different scales. The formula there you see for the z, one is on the left for a population value, and the z on the right is for our sample. And that really should say, just noticing that there's a typo here, x minus x bar, which is the mean, over the standard deviation. Okay, and we'll do a few of these in class, but what I want you to know is that there are three properties when we talk about z-scores. Okay, the mean of all z-scores is a 0, which also means the sum of the scores are 0. Standard deviation and variance are both 1, and this is considered a linear transformation. So what we are trying to do is to bring two scales that are very different to a similar mean and standard deviation point, and we'll show you how this is done here in just a second, so that we can then compare apples to oranges. Okay, so let's go back to our ACT and GRE example. Let's say we have a student who gets a score on the GRE of, let's say, 24. I don't know, we're just making this up. Okay, let's say that this is the student's score on the GRE. Okay, what is the mean? And we could look this up. I probably should look this up before making the video, but I didn't, so we're just going to make up some mean score here. Let's say the mean of the ACT is 19.6. I think that's what the mean was when I was in school. It was out of 36 instead of 35, so I'm sure this is different nowadays. And let's say that the standard deviation on the ACT was 3. Again, I don't know. We're making it up, but we're going to say this is what it was. Okay, so now I've got a participant who got a 24 on this ACT. And let's say on the other hand, I've got a participant over here who got a 170. Maybe that's out of range here. Let me pull this over a little more. Let's say participant number 2 got a 170 on his GRE. Okay, and let's say that the mean on the GRE, again because I have no idea, we'll say that the mean of the GRE is 150. Okay, and we'll say the standard deviation is 10. Okay, now the question is, who scored higher, relatively speaking? Was it the guy with the 24 or was it the gal with the 170? I don't know. We're going to have to transform these data in some way to make them meaningful. We can do this through what we call the z-score transformation. So let's work through this formula real quickly. So I can take, in this case, the x, which is 24, minus the mean, which is 19.6, and I can divide that by the standard deviation, which in this case is 3. So if we take this, What's 24 minus 19.6? We're going to get 4.4, correct? Divided by 3. So what is 4.4 divided by 3 is 1.2. What is that? 1.2. My brain is blanking. 12, 20. 1.2. Let's just say 7. Okay, close enough. I may be off, but we're going to go with 1.27 since I don't have my calculator in front of me. Okay, so now we know that this z-score for a 24 on the ACT is 1.27. Now let's calculate a z-score for this GRE score. So now I've got 170. I'm going to subtract my 150. Okay, and now I'm going to divide that by 10. So now I have 170 minus 150 is 20. 20 divided by 10 is 2. So the z-score for this GRE is 2. The z-score for my ACT is 1.27, which is greater. The GRE has a z-score of 2. So an individual who scores a 170 on the GRE is doing better than the individual who scores 24 on the ACT. Hopefully that makes sense. We'll use this as we go forward.